Hello, and welcome to the AI in Medicine course. My name is Pascal, and I'll be your guide as we travel through the world of artificial intelligence and machine learning as applied to the area of medicine over the next few months. This course is geared to those of you in medicine who have an interest in learning about artificial intelligence and machine learning, possibly adding it to your research, or simply just understanding when you hear of it in the clinical setting. Okay, a little bit on who I am. I'm an associate professor in the Department of Medical Imaging in the Faculty of Medicine at the University of Toronto. I'm also appointed to the Institute of Medical Science, as well as the Department of Statistical Sciences. Inevitably, my interests lie in medical research, of course, and how artificial intelligence, machine learning, as well as classic statistics or biostatistics can be applied in order to further research. Okay, just a few disclosures. I'm the CEO and co-founder of a software company named SoftX Innovations. I'm also the Chief Science Officer for a medical device company named AceAge. I've also served as a consultant for the pharma company Novo Nordisk, and I have industry partnerships in the area of artificial intelligence and machine learning with a company named 16-Bit, as well as IBM Watson Health. So way back in 1980, when I got started with this whole concept of computers, I received from my parents a Commodore VIC-20. I don't know if any of you remember the Commodore VIC-20. Maybe some of you are chuckling, thinking, oh yeah, I had one of those. It was very limiting, of course, with only 5 KB of RAM. Wow. However, it was a lot of fun, and I was able to learn my first computer language, which was BASIC. And hours and hours of fun. Of course, what happened is I ended up exceeding the memory capacity of the computer with one of my programs, and from that moment on, I kind of went, time to move on. And at the time, there weren't very many better computers that we could afford, so I kind of had a gap after that until I was able to get another computer that enabled me to do more. So, how many of you can put your hand up wherever you are, still have an iPhone 6? Now, the reason I ask is because this on the right of the iPhone 6, if it looks familiar to some of you, is a supercomputer. And it is a supercomputer from IBM called Deep Blue. If you compare the size of the iPhone 6 to Deep Blue, I just showed you on the screen, it's tiny, right? So Deep Blue is a very, very big computer. It stands over 6 feet, and it was a big achievement for IBM, because in 1997, Deep Blue defeated Garry Kasparov, who at the time was one of the leading chess masters of the world. And so this kind of was a landmark moment where a computer was actually able to do something better than a very skilled human. So my question to you is, which of these two devices, the iPhone 6 or the Deep Blue supercomputer, has 142 gigaflops? So gigaflops, or flops, is a measure of compute power, speed, capacity. I'm not going to go into the detail of what a flop is, but you can just imagine it's just a unit of that we use in order to measure computer power. So which of these two has 142 gigaflops? Normally in my presentations, I ask you to lift your hand what you think, but inevitably, I would imagine you can guess that I'm leading you on, and essentially the 142 gigaflops belongs to the iPhone 6. And you can imagine the iPhone 6 is already outdated. So just consider what you have in your pocket is much updated, and therefore would be much greater in gigaflops. And compared to the Deep Blue, which had 11.4 gigaflops, you have a supercomputer in your pocket. And it is for that reason that artificial intelligence and machine learning is making such a big splash, because now we can perform or run the algorithms that are necessary for this artificial intelligence. And of course, we'll talk about all of that in this course, with the computers that are available to many. And that's one of the big reasons that artificial intelligence is now available to us, because we have the capacity to run these complicated algorithms, and we have access to relatively cheap storage, which is required for all the data we would need. Okay. So other than this being a very cute kid, there's a wonderful quote by Edward Fredkin, and he says, there are three great events in history. One, the creation of the universe. Two, the appearance of life. The third one, which I think is equal in importance, is the appearance of artificial intelligence. Now, Edward Fredkin was a former manager of the MIT AI laboratory. Of course, a little bit of tongue-in-cheek here, but it does kind of drive home the idea that artificial intelligence truly is a big thing, a disruptive technology, and we'll talk about that a little bit later. Another great quote from the medical field is, we need to take the artificial away from our embrace of the technology. The term AI should stand for Augmented Intelligence. I like this quote simply because I do believe it, that this whole concept of artificial intelligence really should be considered as augmenting what we currently have, what we're currently operating at. Another great quote, this one from a radiologist: I don't see AI as competitive, but rather as an augmentation and expansion of the radiologist's capabilities. Once again, I also agree with this strongly, because those radiologists that think that artificial intelligence is going to replace them, those radiologists, I would suspect, are not willing to make change, because artificial intelligence is going to provide tools that are going to allow the radiologist to do more quicker, and also, more importantly, to do different things. So the job of the radiologist is going to change over time. So they're not going to lose their job. It's just that their job's going to change, and hopefully for the better. So why are we so smart? Well, we've survived billions of years of evolution, and we have evolved into the species dominating the world. I'm not sure necessarily that's all of a good thing, but our intelligence has contributed to us being able to be the dominant species. Now we learn from our mistakes, or we're supposed to. My wife always chuckles when she sees this slide. And we do adapt ourselves to perform better. Now that's something that drives us, that we always want to do better. We always want to improve our performance. How about artificial intelligence? Well, let's start with the definition of intelligence. It's the ability to acquire and apply knowledge and skills. Okay. Now, way back in 1956, the AI pioneer McCarthy coined the term artificial intelligence at a conference, actually. And he said it was the science and engineering of making intelligent machines. So meaning machines that would have the ability to acquire and apply knowledge and skills. Perfect. So what do you need to remember when anyone brings up the term artificial intelligence? Is store, compute, and learn. In a nutshell, That's what artificial intelligence is doing. And just as I talked about in the previous slides, cheap storage is very important. The ability to compute, so compute capacity is extremely important. That's what those are the two factors that have enabled us to jump into this world of artificial intelligence. And finally, there has to be some learning. Okay, so here's the beginning of the fun. So the AI spectrum. So what comes under artificial intelligence? Well, a lot of stuff. The most, I guess, noticeable would be the machine learning. You see here, up here at the top, you have machine learning, you have supervised, unsupervised, and reinforcement learning. Okay. You also have natural language processing. That one I'm sure you've heard of as well. A lot of that is like, the Google Translate and all that fun stuff, and, word checking and correction, which sometimes can be extremely annoying. But you also have other areas which, probably don't come up as often, right? Which is expert systems, vision, which would be image recognition, machine vision. Of course, that one's important to those of us in radiology. And usually you have a combo between the vision and the machine learning. You have speech, which is the speech to text, text to speech, of course. Planning, which is in more the administrative, but it's very important. And robotics, of course, if you're an engineer, robotics is it, for artificial intelligence. You're going to be talking about robots. All right, so this figure here is an interesting one, or graph. It shows on the x-axis time, and then on the y-axis performance. And this would be performance of a technology. Now, if you look at, what's called low quality use, medium quality use, high quality use, or like, wow, most demanding use, those are just levels of essentially your technology, the use of the technology. And you'll see that as, when it's extremely demanding, you have to have, high performance for it to be acceptable, right? And you can see that, something, all four of them are parallel in terms of their, relationship with time. So as time increases, so the, more time, goes along, all of these, no matter if it's a low quality use technology or a very high demanding use technology, they all improve with time. Performance improves with time. Now, you'll see this one last line that is, somewhat exponential in terms of growth, and it's termed disruptive technology. So a disruptive technology is one that over time, the performance will just outstrip anything else in terms of its use. So meaning it's going to start off as something that's like, kind of low, really low performance, but over time it's going to end up like, wow, crazy high performance. And so an easy way to remember this is a 10 times improvement in performance in less than 10 years would be considered a disruptive technology. So you see in brackets here, I put Blockbuster and Kodak. So it's not Blockbuster and Kodak that are, the disruptive technologies. It's the disruptive technologies that knock those big giants out. And so Blockbuster, of course, is Netflix. So Netflix started off as this. Actually, they started off in shopping stores, right, shopping malls, with DVDs, right? That's actually how they started. But inevitably, what they've turned into is a disruptive technology. So in less than 10 years, they've just taken it over, right, basically. And Blockbuster is gone, and Rogers and all that. Kodak's another one. Kodak was the leading film company in the world, and they didn't anticipate that digital media for photography was going to become a thing. And what happened was they're gone. They're literally gone because they didn't plan. They tried to jump in the game at the end with digital cameras, but they were too late. Anyway, there you go. AI, in my opinion, is going to be, if not already, a disruptive technology. So there's also the fourth industrial revolution. So this one you have to go back to your high school days when you learned in history, about industry, and how, in the 1700s, you had mechanization, steam power. And of course, for textile, you had the weaving loom, which was a big deal, right, to make clothes. And that was that's what the industry was at the time. And then in the 1800s, you moved on to, what was called mass production, assembly lines, electrical energy. So that one, that's Ford, right? The Ford Model T, right? That classic assembly line. And then we move on into the 60s. Now I'm alive. Uh, and you have automation, you have computers, and you have electronics, and that was a big deal. I remember, back then, with my VIC-20, I was very excited, but that was a big deal. And then you had, video, you watched videos. TV had been around forever, of course, and radio, but the ability to pop your VHS and watch a movie and go to go to Blockbuster was wow, like that was a big deal. So today, though, we're looking at the fourth industrial revolution, and this one is going to be basically the internet and networking. So it's going to be communication. So it's the Internet of Things, the network, and what's called cyber physical systems, which is just describing our current phase of the industrial revolution. And that one is important to keep in mind because you almost take it for granted that you have this access to this wonderful network and this ability to communicate. But that is a very important component to understanding, artificial intelligence. Okay, so let's get back to some definitions. General definition for artificial intelligence is the capability of a machine to imitate intelligent human behavior. We've already seen this with McCarthy. AI uses computers to model intelligent behavior with minimal human intervention. So that's the key. So it's not only modeling intelligent behavior, sure, but there's minimal to no human intervention. Now, just to go back to the history of AI, as I've already alluded to, John McCarthy during a conference coined the term, and the possibility of machines being able to simulate human behavior was actually raised earlier by Alan Turing, and his time was Second World War. So that's when he did a lot of his work, was during the Second World War and just after the Second World War. And he developed the Turing test in order to differentiate humans from machines, and he's known for that as well. So just all of this just to say, it's not a new concept. It really, truly is not a new concept. What is new is our ability to leverage it, to actually start work in the area, because compute power, cheap storage. All right, once again, artificial intelligence, machines that are programmed to mimic the way that humans think and produce actions, decisions that simulates that of a real person. So, if machines simulate what humans do, would they have our intelligence? There is a good question for you guys to think about, and maybe that's something we can discuss during one of our discussion sessions. So modeling the human brain, the brain, brains function as the result of an immense number of neurons firing signals. Okay, so this is just physiology, right? Neurons connect through synapses, which propagate electrical impulses by releasing neurotransmitters. So in a nutshell, that's how our brain works. Now, the synapses' plasticity allow for learning. So long-term changes in connection strength can be made through these synapses. So how does this neural structure lead to thought and perception? We don't know. And there's the rub. We're still trying to figure that one out. Neuroscience has made several pivotal contributions to AI development. And a researcher from MIT, Odd Oliva, stated, the fundamental questions cognitive neuroscientists and computer scientists seek to answer are similar. They have a complex system made of components. For one, it's called neurons, and for the other, it's called units. So neuroscience studies how the brain works in order to create recognizable behaviors. And neuroscience theory believes individual neurons are fairly simple, and the information required for processing complex concepts is distributed across multiple neurons. So many, many, many neurons. The artificial neural network loosely follows this second theory. An artificial neural network, so ANN, mimics the biological brain in the sense that it acquires knowledge through learning and stores this knowledge by adjusting the weights within the network. In 1943, neurophysiologist Warren McCullough and mathematician Walter Pitts described how neurons in the brain might work by modeling a primary neural network using electrical circuits. And in 1949, Hebb describes if one neuron repeatedly stimulates a second one, then the connection between them will strengthen. And this is the notion of synaptic strength that is represented by weights in an artificial neural network. Now in 2012, this was the first year that neural nets, so neural networks, grew to prominence as 3 researchers from the University of Toronto, including Geoffrey Hinton, of course, used them to win that year's ImageNet competition, which is basically the annual Olympics of computer vision. And they did so by dropping the classification error record from 26% to 15% in a single year, in a single competition. And this, of course, is an astounding improvement for the time. So let's just talk just briefly a little bit about neural networks. Now, they try to mimic how the brain works, as we've just seen in the previous slides. They simplify neurons to units, also called nodes, that are linked in layers. So you can see in this little fun figure that you have vertically, the dots represent layers. In this one, you have a single input layer, a single middle hidden layer, and a final output layer. And this is a classifier to classify animals into dogs or cats. So nodes are comparable to old men with hearing difficulties standing at a distance from each other. Now, it could be old women, of course, but I chose old men for this example. And they only hear when the sound is loud enough. All right. Neural network units or nodes. They're comparable, as we've just seen, to the neuron, where the neuron has a cell body with a nucleus, of course. It has the dendrites, which is its input, the axon, which connects us to the terminals, the axon terminals, which is its output. Now, the neural unit, network unit, or node, is very similar, where let's say we have a unit U. Each link has a weight and an activation level, and each unit has an input function, an activation function, and an output. So let's say, as you can see here, we have a bias, which is an additional constant that we use and is added to the weighted inputs, as you can see on the left, input 1, 2, and n, right, for the activation function. The input function is applied to the weighted inputs before the activation function. And the activation function calculates a weighted sum of inputs and bias. Now your output on your right is calculated based on the bias, the inputs, and the activation function. And this is passed on to the next linked unit, or if it's in the n layers, outputted as the model's prediction in the final unit. Now this is just a high-level overview of how neural networks work. The only reason I'm talking about it now is just because it's interesting in terms of comparing it to the brain and its neurons. So why machine learning? Well, many problems are difficult to program rules for. For example, computer vision, speech recognition, medical image analysis. I mean, you can see immediately that, these three that I've just enumerated are, where there's a lot of research in artificial intelligence and machine learning. And that's because they're very complicated problems. Now, some systems need to adapt to changing tasks or environments. So if it's constantly changing, it's tricky to set rules for it. A good example of that is spam detection. Wow, that's changing hourly, constantly changing. Robot movement. How do you adapt to your environment when you're programming a robot? So there's another couple of examples where machine learning and artificial intelligence have made huge progress in those areas. Now, machine learning can find patterns in large amounts of data. And that's where the compute and the storage comes into play, because being able to find patterns is nothing new. However, being able to find patterns in just ridiculously large amounts of data, and very complex patterns, and many of them, is something that lends extremely well to machine learning and artificial intelligence. So machine learning is essentially a set of algorithms. If you're from the world of statistics, you could call them models. And the goal, the purpose, for example, is to find patterns in existing data. And you modify parameters of these algorithms to best describe the data pattern of interest. And performance improves as the amount of training data increases. I'm sure you all have heard that before. Now you can also make predictions or decisions. And what you hope to do is, based on your model, is to be able to make these predictions as decisions on new data taken from the same population as the trained data, and do so accurately. Now you're of course using the algorithm, which in this sense you could consider it the pattern, found in your previous training, so from the training data. So how do these magical algorithms allow machines to learn like humans? Well, one way is by describing what's called the cost function. It penalizes mistakes that machines make. The larger the cost is, the more the machine adjusts or must adjust its parameters in the algorithm. So learning in this case could be compared to minimizing the cost function. You can see here in this little figure that on the x-axis is the number of iterations of building your algorithm, and on your y-axis is the cost function value. And as you can see, through this iterative process, what you're doing is you're minimizing the cost function as you improve your model. Another aspect of learning is with the Presetron learning rule. So in order to train a neural network, a batch of trained data is used, of course. Now, during each batch of processing of the training data, if the output is correct, we don't change any of the weights because it was correct, it's right. However, if the output is low, what's considered low, we increment the weights, so we adjust the weights for all inputs which are 1. If the output is high, which is just literally the other direction, we decrement or adjust down the weights for all inputs which are 1. Another form of learning is through backpropagation. It's similar to the perceptron learning algorithm. However, while we're iterating through the training data, if the output network is correct, we don't change anything, of course. But if there is error, we propagate back to the previous layer and modify the weights of that layer. And the weight modification is performed through different optimization algorithms. So there's different ways of modifying the weights for this backpropagation, and these are called optimization algorithms. Okay, let's stop there for a minute, pause, and talk a little bit about the nomenclature of machine learning. So you can see here in these two circles that machine learning is contained within this label called data science, and we're going to talk about that later on in this lecture. Now, in a few slides back, I mentioned that machine learning, there's three big chunks. It's supervised learning, unsupervised learning, and reinforcement learning. I'm going to talk about just the two more used types of machine learning, which is supervised learning and unsupervised learning in the area of medicine research, medical research. Supervised learning is clearly the most approachable form of machine learning because it involves classic prediction. You want to predict something. For instance, in the case of a binary output, so yes, no, two levels, disease, no disease, cancer, no cancer, that's called classification. There are many algorithms, machine learning algorithms that can help you perform classification. SVM, support vector machines, discriminant analysis, and of course what we just talked about, neural networks. But if your outcome is a measure, a continuous variable, then you would use regression. And of course you can just use simple linear regression. You can use decision trees, but once again, you can also use neural networks. Interesting. Now, if your data isn't labeled, right? So it hasn't been classified into groups for you in order to perform classification, or in the case of a continuous variable, the measure hasn't been assigned, right? So let's say you're trying to predict weight, body weight. Well, everyone in your training set would have an assigned body weight, and then you would build your algorithm around that. But let's say you don't have that measure. You're not quite sure how to meaningfully divide your data into clusters. And so that is called unsupervised learning. And unsupervised learning will look to try and group your data into meaningful clusters. And that's actually an area of mine of interest. And some of the approaches, which are classic, is k-means, fuzzy k-means, hierarchical, clustering techniques, and there's a bunch of others. But interestingly, neural networks is also contributes to this area as well. And so interestingly, neural networks, and that's why they're so popular, is actually quite adaptable. And so quite an interesting algorithm to consider. And that's the reason I've already introduced them. And we're going to talk a lot about neural networks, throughout this entire course. So when I talk about neural networks and I tell you they're very adaptable, there's one other piece that I want to bring out here. And then here, now there's three circles, okay? So we have artificial intelligence, and artificial intelligence would come under data science, right? But artificial intelligence is simply a program that can sense, reason, act, and adapt, right? Underneath or within artificial intelligence is machine learning, which are algorithms whose performance improve as they're exposed to more data over time. That's the learning aspect of it. So here's this other term that I'm sure you've heard all the time, and that is deep learning. So deep learning is a subset of machine learning, but in this case where you have a multi-layered neural network that is learning from large amounts of data. So if you remember when I showed you the neural network, or the ANN, artificial neural network, I had an input layer, I had a middle layer, and an output layer. Well, if you were to increase that middle layer to many, 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 many layers, then you have what's called deep learning. All right, this brings us to the end of the first lecture. Why don't you get up, walk around, stretch your legs, and we'll see you back for the second lecture where we'll talk about the different types of machine learning.